So the next thing we're going to do is talk about bond theory and how do these Lewis structures get, how do we see what the actual molecule looks like from these Lewis structures. So we're going to talk about the geometry of a molecule. There's two theories of chemical bonding, valence bond theory and molecular orbital theory. We're really, in this class, only going to focus on the valence bond theory. Molecular orbital theory is actually probably a little bit more correct and but it's a little bit more complicated. And if you go on and take more chemistry, you'll probably learn molecular orbital theory, but we'll stick with valence bond theory for this class. Molecular geometry is the general shape of a molecule. So it's determined by the positions of the atoms in the structure, so the relative positions of the atoms. So what is the valence shell theory? So it's actually called the VSEPR theory. VSEPR stands for valence shell electron pair repulsion theory. Or model, and it predicts the shape of molecules and polyatomic ions by assuming that all the electrons, all the valence electron pairs, remember electrons don't mind hanging out in pairs because they have the spins where they kind of hide from each other, but every pair then wants to be as far apart from the others as possible. So you know, electrons repel each other, so the pairs know how to hide from each other, but all the pairs of electrons around the central atom want to be as far apart as possible. So we're going to look at the different arrangements of the electron pairs around the central atom, and it will depend on how many electron pairs there are. Now, so sometimes we use balloons because electron clouds are sort of shaped like balloons, and so we can see how they arrange themselves according to the VSEPR theory. So this is kind of a nice little picture. You can see that if you have two electron clouds, they want to be as far apart from each other as possible, so they kind of make this linear shape. If you've got three pairs, then they're going to have to make this triangle shape. Because we're thinking so far those are 2 and 3 dimensional, but because we're thinking 3 dimensional, if you have 4 pairs of electrons, this is how they will naturally form themselves, and kind of make like this where it's coming out. So this is called the tetrahedral shape. If you have 5 pairs, this is what it looks like. You can see that there's actually like a triangle around the center, and one up and one down. And then if you have six regions of electrons, and remember atoms can have up to 12 electrons, so that would be six electron clouds, then this is called the octahedral. It's kind of funny because it's 6, but it's called the octahedron, and that has to do, I think, with how many faces the structure has. But anyway, there's 6. So it kind of makes a square, and then one up and one down. So that's called an octahedron. So those are the 6 electron pair arrangements. And then it will depend. So it will depend on whether the electrons are bonded or non-bonded. So what we're going to do, once we draw our Lewis structure, which we've just got through learning how to do, we're going to draw the Lewis structure. Then we're going to determine how many electron pairs are around the central atom. You want to count them all. Now, there's a couple of things to keep in mind. A multiple bond actually only counts as 1 pair, and that's because they really take up 1 region. You know, if you've got a multiple bond, it's still only 1 region because the 2 atoms are the 2 are the same on both ends. So we only count a multiple bond as 1 electron domain. So sometimes I like to electron pairs, or sometimes I'll call them a domain, like I said earlier. So an electron domain, any bond is considered a domain. So any single bond, any double bond, any triple bond is counted as 1 domain. And then any unshared pair is also counted as 1 domain. So you want to make sure, count all the bonds, and then make sure and count any unshared pairs. And then there, like we said, what I just showed you, then they're arranged. So again, linear has 2 electron domains. And so now I'm going to start introducing a few other things. I want you to know the bond angles and the names. So if you have 2 electron domains, and it doesn't matter if they're bonded or non-bonded yet, we'll talk about the difference in a minute, but 2 pairs will be called linear, and the bond angle is 180 degrees, as you can see here, 180 degrees from one side to the other. 3 pairs will be called trigonal planar, because there are 3, makes a triangle, but it's all in the same plane, so it's flat, and the bond angles are 120. If you have 4 pairs of electrons or 4 electron domains, they are tetrahedral, which is 109.5 bond angles. If you have 5, this is called the trigonal bipyramidal. The trigonal bipyramidal is the only one that has 2 different bond angles. So it's, like I said, it's got this triangle around the center, and those bond angles are 120 from one end to the other of the triangle. And then going up and down, they're 90 degrees. So the 120 and 90 degrees. And then finally, if we have the octahedral shape, which has six points, and so it's like a square with one up and one down, and all bond angles are 90 degrees. So this is, I think, from your book, and so again, this is the same thing that we had. So 2 regions of electron density, or electron, either a bond or an unshared pair in a region, electron domain, I like to call them. It would be, again, 180 linear, 120 trigonal planar for 3. 4 is tetrahedral, 109.5. 5 regions is called trigonal bipyramidal, because there's a pyramid going up and a pyramid coming down with a triangle around the center, and again it's got 90 and 120 degree angles. And then finally octahedral has the 90 degree angles. And here you see a few examples of molecules that have that shape. So beryllium, if you remember, I said earlier, it's one of the exceptions. It likes to only make 2 bonds, and so it's linear. Boron with 3 hydrogens is trigonal planar. Carbon with 4 hydrogens is tetrahedral, and phosphorus with 5 fluorines is trigonal bipyramidal, and then sulfur with 6 fluorines is octahedral. And we're going to look at a whole more examples in just a minute. So once we have our Lewis structure, the first thing we want to do is figure out how many domains there are. So total, remember we said total domains are total number of bonds of any kind, and total number, add to it the total number of unshared pairs. So we're going to find out what the molecular geometry is. And so the domain geometry are those that we just showed you, but the molecular geometry may be a little bit different, because we have to distinguish between bonding electrons and non-bonding electrons. So what we just saw, those 5 shapes that are considered molecular domains or electron domains include unshared pairs and bonds. And so those are the overall domains. But once we have the overall geometry, what we're going to do is we're going to kind of drill down and look and see what the unshared pairs do. Since the unshared pairs don't have an atom attached, they actually don't take part in the molecular structure. So you'll see what I mean in just a second. So here's some examples. So linear, again, is pretty easy because it's got 2 bonds, and that's it. Now, so if you have a total of 2 electron pairs, both of them are going to be bonding, and it's going to be linear. If you had any unshared pair, then that would mean you only have 2 atoms, and of course that would stay linear as well. Now, if you have a total of 3 domains, so a total of 3 either bonds or unshared pairs, we have a couple of options. Either all 3 of them can be bonded, so that's this shape here. So that's the trigonal planar. So if all of the total are bonding, then we get the original domain shape. So if all 3 are bonding, we have this trigonal planar shape. But what if only 2 are bonding and 1 is unshared pair or lone pair? We end up with this shape. Now you can see the overall structure is the same for whether it's 3 or 2. But because there's nothing attached up here, the actual molecular shape is this right here. Where here, this is the whole molecular shape. Here, this is just the molecular shape. So again, the domain shape is trigonal planar. The arrangement of the pairs or the domain shape is trigonal planar. However, the molecular geometry is just called bent because it's just this part right here. Just if you're looking at the SO2, it's just that part there. So even though those electrons are hanging out there and they're forcing these oxygens to be closer to each other, so it's forcing it to have that bent shape. However, the actual molecule, you don't see the unshared pair. You'll be doing an exercise online which can help you see this as well. So that's 2 and 3. Now 4, again, if all 4 are bonding, then we have it's 4 overall. The 4 domain is tetrahedral. And if all 4 are bonding, then we have the tetrahedral because, again, we have this, this shape. So all 4 bonds tetrahedral. But if only 3 of them are bonding and 1 is an unshared pair, you can see here you have this shape right here. The overall shape is still tetrahedral. It's just that the molecule itself, you only see this bottom part of it, which is called trigonal pyramidal or trigonal pyramid. And then if you only have 2 bonds and 2 unshared pair, then you have what's called bent. Actually, you could also draw it like this, so it kind of looks like this with the unshared pairs kind of going in and out. I'm not a very good drawer, but it's that bent shape. So now we're drilling down. So if I say what's the domain shape, it would be 2 is linear, 3 is trigonal planar, 4 is tetrahedral. But then if I say what's the molecular shape, then we drill down and we have to know how many. So there's 4 domains, how many are bonding, how many are non-bonding, and we get these shapes. 5. So you can see we have even more choices. So if all 5 are bonding, whoops, that was kind of funky. If all 5 are bonding, then we have the overall structure, which is called trigonal planar. I'm sorry, trigonal pyramidal, which looks like, it's got a triangle around the center and then one pyramid going up and one pyramid coming down. If only 4, now this is important, one more thing. So if all 4 of them, on the last slide, it didn't matter where the unshared pairs went. On the structure with the 5, it's important where the unshared pair goes. So if you have 4 bonds and 1 unshared pair, the unshared pair or the lone pair always goes around the center. So notice that I've never put it on the top or bottom, and that's because they like to take up the most space. And since the bond angles around the center are 120 degrees and the bond angle up and down is only 90, they're going to always want to take a center space. So you can see here, and I think if we do this in lab, you'll see better. This is called the seesaw shape. It kind of looks like a little, if I draw it this way, you can kind of see it. It kind of looks like a seesaw where it kind of can rock back and forth because the unshared pair is right here. And so the 4 bonds, 1 unshared pair is called a seesaw. If you have 3 bonds and 2 unshared pairs, the 2 unshared or lone pairs are around the center, so you end up with a T-shaped. And this is kind of, two-dimensional because the electrons are coming out, but the 3 molecules are in the same same plane. And then if 2 of them are bonding and 3 are unshared pair, all the unshared pair are around the center, and you get the linear shape. So again, what's the domain shape for 5? Trigonal bipyramidal. But then we drill down, and depending on how many lone pairs and how many bonds we have, we come to the other shapes here. And then finally, we've got the 6. So 6, in this case, again, it doesn't matter where the first unshared pair goes. So again, the overall shape is octahedral. So if you have all 6 bonds, then the shape is octahedral. If you have only 5 bonds and 1 unshared pair, you have what's called a square pyramid. It doesn't matter where the lone pair goes because all the bond angles are the same. So you can see here it's a pyramid, but this time the bottom is square, so square pyramidal. When you have a second, for this one, when you have a second unshared pair, then it has to go opposite the original one because, again, they like to be as far apart as possible. So you end up with what's called square planar. So the unshared pair is top and bottom. And then actually we can do a few more. If you have 3 and, wait a second, yeah, 3 and 3, you'll get the T-shaped again. Looks like that. And if you have 2 and 4, you'll end up with linear again. So, but these are probably the 3 important ones for 6. All right, so this is a nice little chart. I think when we do the lab, we'll have this chart as well. And so this tells you, so total number of electron regions, 2, 3, 4, 5, 6. The electron domain is the same as if all of them are bonded, then the electron domain and the geometry are the same. And so here you have your bond angles. If you have 1 lone pair, of course, if it's 2 and 1 lone pair, there's no structure. But if you have 1 lone pair, it's bent. 1 lone pair with 4 is trigonal pyramid. 1 lone pair with 5 is the seesaw. And 1 lone pair with 6 is square pyramid. If you have 2 lone pairs, that can only happen if you have 4 domains. That's called bent. Excuse me. If you have 2 domains and 5 total domains and 2 unshared pairs, it's T-shaped. If you have 6 domains and only 2 unshared pair, then it's square planar, and then linear, T-shaped, and linear. Anyway, you can study that. So let's just do a few examples. If we predict the molecular, here's what 2 looks like. So if I look at that carbon and I say, okay, how many domains? And don't get confused with these little electrons on the outside. We're only looking at any central atoms. So in this case, carbon has 2 domains, because a double bond, remember, just counts as 1 domain. So a double bond counts as 1 domain and another one 2 domains. So this is 2 domains, and as we know, 2 domains is linear. So the bond angles are 180 degrees, and the domain shape is linear, and the molecular shape is also linear. So let's look at this one. Notice that the carbon has no unshared pairs on the center, and it has 3 bonds. So this is the overall domain with 3 regions is called trigonal planar, and because the geometry is also because all of them are bonds and no unshared pairs, then the overall geometry is also trigonal planar. And that's why when I drew it way back at the beginning, you could sort of see it's trigonal planar, because that's just the shape, that's the actual shape it takes. And bond angles are 120 degrees here. Now, this is also 3 regions. So this oxygen has 1 region, which is a double bond, 1 region, which is, I guess I'll put a 2, another bond, so 2 bonds and 1 unshared pair. So that is 3 regions. Unshared pairs take up space just like a bond, and so you have to count them. So this has 3 regions. So its overall domain geometry is trigonal planar. So it's got the 3 domains, trigonal planar. But because it has one unshared pair, we're going to call this bent. So ozone is trigonal planar domain arrangement or overall electron pair arrangement, but we also call it because so bent because it has the unshared pair. And you can see that that shape is bent. So if we, sometimes I'll draw the unshared pair sort of in a little bubble to remember that it ends up taking space. So that, but there's nothing, you know, there's nothing attached up here, and so the overall molecular structure is bent. Right, so the electron pair arrangement includes the lone pairs, but the molecular geometry does not include the lone pairs in the overall shape. All right, so let's look at 4 electron pairs. So you can see the first one, the carbon has 4 bonds. So that's considered tetrahedral. The nitrogen has 3 bonds and 1 unshared pair. So again, it has 4 electron domains. So again, tetrahedral. And then the oxygen has 2 bonds and 2 unshared pairs. So again, tetrahedral. So all 3 of these have the tetrahedral electron pair arrangement. However, they have different molecular geometries, and I'll draw them in a second. There we go. So the carbon with all 4 bonds is also tetrahedral because there are no unshared pairs. So the molecular geometry is the same as the domain geometry. The ammonia, NH3, has the trigonal planar because, again, we don't count this up here in the geometry shape. So we just have that trigonal planar. And then, and so you can see that the oxygen is bent. Notice that this is kind of a common way of drawing it, that wedges mean that it's coming out at you. Dashes means it's going away from you. And so that's kind of going away from you and coming at you. Let's look at a different example. So here's got 5 electron pairs, so the trigonal bipyramidal. And so you can, in this case, we've got all 5 bonding. And so trigonal bipyramidal, both domain geometry and molecular geometry. And remember, it's got 90-degree angles and 120-degree angles. Actually, if I were to draw this now, let me use a different color. It's a little bit lighter. If I were to draw this, let's erase that. Okay, start over. If I were to draw this, I would put 1 up, 1 down, and then notice the circle. So if I do my dashes and wedges, that one's in the same plane, but then it's probably a little better if I did a wedge and then a dash. So now you can actually see a little bit better the triangle around the center. So again, with 5 bonds, it's trigonal bipyramidal geometry as well. Other molecular geometries with 5 are possible. So let's look at so you can see here sulfur has 5, and remember we're only, now there should be unshared pairs on the F's, but since they're not they don't have anything to do with the geometry of the center, so that's why they're not here. But we do want to see how many lone pairs are on the center atom. So the sulfur has 4 bonds and 1 unshared pair, so we call that the seesaw. And again, if I were drawing it, I'd probably draw it like this, and I would probably put a wedge with that way and a dash with that one, just to sort of see it. So that's the seesaw. Now the T shape, this is fine. I'd probably alter that and put that as a wedge and that as a dash, or the dash or the lines like that can represent going away. So 3 bonds and 2 unshared pairs is considered T shape, and then 2 bonds and 3 unshared pairs is linear. And then finally, we have our 6 electron pair, which is octahedral. And again, even though, so this case, all 6 are bonded. So this is the domain, the domain structure, the domain geometry is octahedral, and also the molecular structure is octahedral. And just to be a little more clear with my drawings, let me draw it here for you. So these actually go away. This one comes forward. The one on this side comes forward, and then this one goes away. So that's probably a little better picture than, or if I had done this with wedges and dashes, maybe would be a little bit better. So square around the center, one up and one down. These bond angles are all 90 degrees. And then here's our some of the ones that have also octahedral arrangement but have different. So our square pyramidal, and again, let's draw that a little better. The F, 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 and then the unshared pair are down here. Sometimes I'll draw like a little bubble around it so you can see the square pyramid. And then the square planar actually, yeah, I would draw it again like this. There's two ways you can draw this. So with the dash is going back and the wedge is coming forward. And then you've got an unshared pair. Interesting, because this is square planar, you could actually draw it like this. And then just show that one of the wedges going that way and one of the wedges is going that way. That kind of is another way of drawing it. So it doesn't really matter. There's more than one right answer. Now, non-bonding electrons, like I said, they're really important and they add to the overall shape of the molecule. But in fact, they do more than that. They actually change the bond angle slightly. What happens is the unshared pair actually likes to take up more space than what a bond would take up. So they kind of like to spread out. And so what happens is they actually push the other atoms a little bit closer to each other. So we can see here that here's the three molecules that have the tetrahedral structure. So carbon with all four bonds is 109.5. So it's the standard angle, bond angle. Ammonia, because it has one unshared pair, what happens is, like I said, these get pushed a little bit closer together. So actually the bond angle is slightly smaller than 109.5 because the unshared pair takes up space. And then the unshared pair here, because we have two unshared pairs, they take up even more space, and they push these a little bit closer together, and so they're 104.5. Now, I don't care if you don't remember these exact numbers. Well, I do want you to know the standard numbers. I don't care if you don't remember the other numbers, but I do want you to remember this effect, that an unshared pair will make it slightly smaller, and two unshared pairs will make it even smaller. So three unshared pairs would make it even smaller. So it's getting a little bit, the bond angles are slightly smaller. Again, this is kind of what I was saying. So bonded electrons get held, sort of pulled in by both ends, whereas an unshared pair likes to spread out, so it does take up more space. And so that's why it pushes the other slightly closer together. The same thing happens with a double bond. Double bond actually likes to take up a little bit more space. And if you go on and take more chemistry, you sort of look at what is the structure of the double bond, and we may be doing a little bit of it later. But anyway, just realize it sort of takes up more space than your average bond, single bond. And so again, what happens is it's pushing these a little bit closer to each other. So you can see that instead of them all being 120, the double bond is slightly bigger, and the single bonds, the bond here is slightly smaller. So again, I don't care if you don't remember the exact numbers, but just remember the effect. What if we have a larger molecule? If we have larger molecules, what we're looking at is we're actually looking at the shape of each center. So a larger molecule actually has, so interior atoms or centers, anything that has more than one bond. So this carbon is a center because it's got 4 bonds. Or just 4 domains, so domains is probably better. This carbon is also a center and it has 3 domains. This oxygen is also a center and it has 4 domains. Now the hydrogen's not a center because it's here on the end, and these hydrogens are not centers because they're on the end. And most of the molecules we've been looking at only have 1 center, but if they have more than 1 center, you can't get an overall geometry. That kind of doesn't make sense. But what you can do is you can figure out what is the geometry of each center. So this carbon here has 4 domains. All 4 are bonding, so it's tetrahedral. Tetrahedron is the noun, tetrahedral is the adjective. So it's tetrahedral, and it has bond angles of 109.5. This carbon in this center has 3 domains. All 3 are bonding, and so it's trigonal planar. And trigonal planar has a bond angle of 120 degrees. Finally, this oxygen has, and remember, it has 4 domains. The unshared pairs count. It has 4 domains, so the overall domain is tetrahedral, but the shape is bent because it only has 2 bonding and 2 non-bonding. And again, the bond angle is, it's actually, as we just saw, slightly lower than 109.5, but you can remember the approximate, slightly less than 109.5. So if you put them all together, this is actually what the molecule looks like. I'm going to actually draw it over here so that you can see. So the carbon is tetrahedral, so I'm going to kind of do that. So carbon's tetrahedral, and it's bonded to 3 hydrogen, and then it's bonded here to another carbon, so that's that. Now this carbon is a trigonal planar, so I'm going to go ahead and make that shape. So it's a trigonal planar. Obviously, one of its bonds is back to the first carbon, and one of its bonds is to an oxygen, and one of its bonds is to this oxygen on the right. So that's the second bond. And then this oxygen, because it's bent, I can just draw it like that, so it's bent. I guess if you drew it that way too, that would be okay. But you don't want to put them straight across from each other because they're not, it's not linear, but it is bent. And then I'm going to go ahead and put little balloons to show the unshared pair, to show that they're kind of taking up space, and that's why the oxygen's bent. So again, this is kind of the overall shape of the molecule. If you have more than 1 center, you can't name the overall geometry, but you can determine the geometry of each center or each interior atom.